What is up, you guys? Welcome to another lecture on optimization algorithms, where the goal is very clear. Given a function f of x, find a point x that minimizes f of x. In this one, I will show you what symmetric rank 1 algorithm, or SR1 for short algorithm, is, and how to use it when combined with the exact line search method. We will approach both methods from intuitive and animated perspectives. A note here is that the SR1 method is a quasi-Newton type method. But not just that, I will also show you how to implement and animate those algorithms on Python. The following video was recorded on NVIDIA's Jetson Orin supercomputer in Abu Dhabi, the UAE, and under a Creative Commons license. I'm Ahmad Bazzi signing in on this one. First, let's talk about the symmetric rank 1 method, or SR1 for short. Let's apply a Taylor series of the function f at xk plus 1 around xk. Its gradient has a Taylor series approximation also as follows. This is obtained by deriving the Taylor series with respect to delta x, which is equivalent to the following linear system bsk is equal to yk, where yk and sk are the drifts of the gradient and the x points respectively. At each iteration, solving the Hessian b is complex. So an update form could be easier. Ideally, what we can do is apply an inverse and we're done, right? But this is complex, especially when we have a lot of variables to treat. Well, instead, we can add a rank 1 contribution on bk plus 1. Said differently, VV transpose is rank 1, right? And we update our equation accordingly just by, adding VV transpose. This is interesting because now computing the inverse of bk plus 1 is achieved by a less complex method. That is, by applying the Sherman-Morrison identity, which is a special case of the Woodbury formula. So tracking the inverses of our Hessian B matrices is easier following this formula. By using U equal to V and BK instead of A, we get the following formula in orange. As we can see, tracking inverses is achieved by simple subtractions, that is, by subtracting each inverse by this fractional expression. Now, the question is, what is sigma and V? Plugging into the equation of our update formula, we get. Expanding and rearranging this gives the following update values of sigma and V, which gives us the SR1 equation update algorithm. First, do a line search to find sk. Then compute the direction using the bk we computed using the rank 1 update. To save computations, we should leverage the Sherman-Morrison formula for the inverse of bk. Update our point in that direction. Compute the sk expression for the rank 1 update, and the yk as well. If our denominator appearing in the SR1 expression is non-zero, then we update using SR1 expression. Else, if it is 0, we preserve the previous value of bk. And we stop according to some stopping criterion like maximum number of iterations, proximity of xk plus 1 relative to xk, or how small the gradient at xk plus 1 gets. Next, let's talk about the line search we are going to use in this lecture, which is the exact line search. For the exact line search, and as the name suggests, we want to find the best alpha that exactly solves the update equation given x and p. Here, x is the point we are standing at right now. So at iteration k, this is xk. And p is the direction we want to take. The alpha tells us how far we go in direction p. So if alpha is 0, we stay where we are currently at. And if alpha is 1, we take a step of p, and so on. To solve this exactly, we derive the first order conditions by setting the derivative with respect to alpha to 0. Rearranging a bit, we finally get the equation p transpose f prime, or the gradient of f, at x plus alpha p is equal to 0, which is the exact line search condition. Perfect! Now let's implement what we have demonstrated on Python. First, let's import some packages that we will be using along the way, like NumPy and SymPy. Then we define an independent function for our line search. For that, we declare a function called exactLineSearch method, which basically takes in the function, the current x value, the alpha to test, and the direction p. And if the exact line search condition is satisfied, we return true, else we return false. Then we implement our sr1 method. Our function will take in the function, gradient, Hessian, and an initializer x0. Even though it won't utilize the Hessian, so you're free to remove the Hessian. The example I am about to show you is a 2D function, hence we have two variables, x0 and x1. So I will store all my variables in x0 val and x1 val, and the evaluated function in fval, which is basically f evaluated at x0 and x1. I will then append the current value I have, where the first value of x0 is stored in x0 vals, and the second value of x0 is stored in x1 vals, and the function in fvals. We define the maximum number of iterations to be 500. We also define the number of variables to the problem to be the size of the input initializer, x0. Let us also define our raw to be something less than 1, let's say 0.55. The sigma as well, fix it to 0.4 and initialize our k to be 0. Initialize bk to an identity matrix, the same bk we talked about in the previous section. Set a very small epsilon to define when to stop taking steps. We will see how in a bit. So this while loop defines the maximum number of iterations, and within I will compute the current gradient. Next, if the direction to take is very small in L2 norm, then it is not worth to continue iterating or walking, as the step size to take becomes less than 10 to the power minus 5 in the L2 norm sense. Next, I will solve the equation bk dk is equal to minus gk to find the direction to take. Please forgive me if I haven't used the Sherman-Morrison formula on Python. I leave this up to you. So instead of doing this inverse formula or the solve function of NumPy, use the closed form Sherman-Morrison formula. Let's initialize m and mk to be 0, then do a line search. We keep shrinking our row by multiplying it with itself or doing row power m each time until the line search condition is satisfied. Then we break and update our x0 to the next value, where we step an amount of row power m times dk. I will now store the current value of x and f of x in the arrays x0 vals, x1 vals, and f vals. Then compute sk as the drift in x and yk as the drift in gradient. Then we check if the inner product between sk and yk is positive. Then we compute b times s and yk minus bs as ys. These terms are intermediate terms in the SR1 update equation. Bk plus 1 is bk plus that big fractional term we talked about in the previous section. We increment k to say that we are going to the next iteration. So that's it for the main loop, and what comes after is really just some printing to show the value we have converged to, and to print the value of the function at the converged point, as well as the number of iterations. Finally, we will return all the stored values. First, let us define counter variables for the number of times we called our function, gradient, and Hessian. It is important to benchmark the number of computations done for any given algorithm. I won't display them here, but it's good if you want to run some computational analysis. Next, let's define our variable through SymPy's index-based method. Then, let's define the number of variables n equal to 2. followed by the function f(x0, x1). It is clear that this function is minimized at x0 equal to x1 equal to 1. Then we compute our gradient and Hessian expressions with the help of SymPy's diff function, which simply performs a derivative. Next, let's generate the function, gradient, and Hessian's Python numerical calculation function using NumPy and with the help of SymPy's lambdaphi function. Then we define the functions as function handles, where fun represents f of x. This is only done to count the number of times we call f of x. For the same reason, I will create a function handle for the gradient and the Hessian. Last, but definitely not least, I will call my function to test how it performs for different initializations. Now, let's test this method for different initializers. It seems to work. Okay, perfect. First, let's create a folder called Animate Iterations, and within this folder, a script called func.py, which contains all my Python animation functions. I will start by importing NumPy. I will create two methods for animating in 2D and 3D. I will start by animate 3D, where I will plot f of x on a 3D axis and show the point xk per iteration in 3D. I will also mark the path taken. The inputs to animate 3D are the function f of x, the axis extreme values of x0 and x1 axis, as well as the x0, x1, and f of x values taken per iteration. I will import some modules in this function like pyplot from matplotlib, axis3d from mpl_toolkits, and animation from matplotlib. Let's create a mesh grid based on the extreme values inputted. The mesh grid will contain 100 by 100 points. Then we evaluate per xy value the z value, which is fx0, x1, and then reshape accordingly. Then initialize a 7x7 figure and instantiate a 3D axis using axis 3D. Then let's plot z versus xy using the following design parameters. Set the x-axis as x0, the y as x1, and the z as fx0, x1. If you're wondering why I have the dollar signs surrounded by the variables, it's because I want to render the symbols as LaTeX expressions. Next, let's rotate the 3D plot to the following view angle. Next, we create the animation where the path then is colored in purple. And the point representing xk is animated as a purple star. Next, we use the following parameters for font sizes of our text. Then we define a callback function, init underscore to initialize our animations where the line and point properties are empty. The text is also set to empty. Following init underscore to, we have another callback function, which is animate underscore to, that takes the iteration number I as input and sets the current value of x0, x1, and f to plot the line and set the point. Optionally, you can have a legend. And before we wrap up this function, we need to generate our animation using animation.funcAnimation. We pass it the current figure and the callback functions animate underscore to and init underscore to. We also set the following parameters like number of frames, which is clearly the length of x0 underscore vals or x underscore vals, since each value represents a frame in our animation. Before closing the function, we show the plot. Then we go to animate 2D, where I will plot f of x on a contour plot and show the point xk per iteration in 2D. The inputs to animate 2D are the function f of x, the axis extreme values of x0 and x1 axis, as well as the x0 and x1 values taken per iteration. I will import some modules in this function like pyplot from matplotlib and animation from matplotlib. So axis 3D is not needed. Like we did with Animate 3D, let's create a mesh grid based on the extreme values inputted. The mesh grid will contain 100 by 100 points. Then we evaluate per xy value the z value, which is fx0, x1, and then reshape accordingly. Then initialize a 7x7 figure and plot the data we have using a contour plot. Next, we create the animation where the path then is colored in purple and the point representing xk is animated as a purple star. Next, we use the following parameters for font sizes of our text. Then we define a callback function init underscore 1 to initialize our animations where the line and point properties are empty. The text is also set to empty. Following init underscore 1, we have another callback function, which is animate underscore 1, that takes the iteration number I as input and sets the current data of x0 and x1 to plot the line and set the point. We now add a legend, if you want. And before we wrap up this function, we need to generate our animation using animation.funcAnimation. We pass it the current figure and the callback functions, animate underscore 1 and init underscore 1. We also set the following parameters like number of frames, which is clearly the length of x0 underscore vals or x underscore vals, since each value represents a frame in our animation. Before closing the function, we show the plot. Now, after we're done with our Animate Iterations module, we import it as follows. Next, we define the extreme values of x0 and x1 axes. We start testing with Animate 2D. We can also test this on 3D animation as follows to see how the method iterates in 3 dimensions. And that's about it. If you enjoyed the video or found anything useful, you can support me by liking my video and subscribing to my channel. If you have questions, kindly leave them down in the comment section below and I'll get to them as soon as possible. I am very grateful for all the support I received over the years, so thank you so much. I'll see you then.